Hello, I'm Seema and welcome to part 16 of the chapter Periodic Classification of Elements. In the previous video, I discussed the periodic trends of ionization enthalpy. In this video, I'm going to tell you about two more physical properties and their periodic trends. These are electron gain enthalpy and electronegativity. Electron gain enthalpy is the opposite of ionization enthalpy. In ionization enthalpy, I told you, the ionization enthalpy is a measure of the energy that is required to remove an electron which is most loosely bound in a gaseous atom of an element in its ground state. And electron gain enthalpy, on the other hand, is the amount of energy that is required or that is released when one electron is added to the outermost shell of a gaseous atom in its ground state. It's basically the opposite. The amount of energy required to pull out an electron was ionization enthalpy, and the amount of energy required to push in an electron into the outermost shell would be known as the electron gain enthalpy. But when you push in an electron and when that electron adds on to the atom and leads to a stable electronic configuration, in that condition it releases energy, and then the electron gain enthalpy in that case becomes negative, because instead of gaining energy, it is energy that is being released. So electron gain enthalpy, unlike ionization enthalpy which only had positive values, this may have negative or positive values, where negative value means that this is the energy which is being given out and it is that much of stability is required, and if it's a positive value, it means energy had to be given to push in the electron, so that was a forced reaction. It wasn't actually something voluntary. You're pushing in an electron and the energy of the system is increasing, which means it's not leading to stability. It's not a favorable reaction. So, electron gain enthalpy can have both positive and negative values, and due to this, the periodic trend is not clear. But on the whole, a general periodic trend can be seen in the electron gain enthalpy. What is the factor that would affect or that would make it easier for an atom to gain electrons? The smaller the size of an atom, the closer are the outermost electrons to the nucleus. And the closer they are to the nucleus, the easier, the more attracted they are to the nucleus. And therefore, when you add an electron which is coming into a shell, a lower shell, it would be easier to push in an electron there. So, electron gain enthalpies should be highly negative for an atom where the electron is being added to smaller shells, logically. Okay, and as the atom increases, the value of electron gain enthalpy should become less and less negative, and at some extent, if you add an electron, instead of becoming negative, it becomes positive. So, it may become positive in the case of electronic configurations where adding an electron, instead of making the atom more stable by leading to a more stable electronic configuration, the addition of electron makes it more unstable in terms of electronic configuration. In that case, the ionization enthalpy would be positive. So, there are some exceptions that we see in the case of ionization enthalpies. And rather, what is the general trend? Let us first see that. As you move from left to right in the periodic table, the size of an atom continuously decreases. And as the size of an atom decreases, the electron that is being added comes closer and closer to the nucleus, and hence it experiences greater nuclear charge or greater attraction from the nucleus. Therefore, as we move from left to right, the electron gain enthalpy, the negative value, should increase. And that is the general trend, that as we move from left to right, we find that the electron gain enthalpy, it increases. Negative value of electron gain enthalpy, not the positive value. So, according to this, we would expect the halogens to have the highest negative electron gain enthalpy. Why? Because halogens have 7 electrons in their outermost shell. By gaining just 1 electron, they acquired the noble gas configuration. The configuration of the noble gas, which is the next element. So, group 17 elements have the highest negative electron gain enthalpies in a period. In a period, if you compare the electron gain enthalpies, the halogen would have the highest negative electron gain enthalpy. And on the other hand, if you see alkali metals would become stable by losing an electron, and that's why they have low ionization enthalpies. On the other hand, if they have low ionization enthalpies, which means you have to use very little energy to remove an electron, doing the opposite would require more energy. So, if you're carrying out the opposite reaction, you're trying to add electrons to alkali metals, you will have to use a lot of energy. So, you are providing energy to the system, so the alkali metals would have positive ionization enthalpies. So, from positive to negative ionization enthalpy, you see a trend. And noble gases here would be an exception again. Noble gases already have acquired their octet. They need not gain or lose electrons. So if you're trying to push in an electron into a noble gas, this electron, the outermost shell is complete. So when you add an electron, this electron would go to the next shell, which is actually further away from the nucleus. And therefore it would lead to an unstable configuration. That is the reason why if you add electrons to noble gases, it would be a highly, you will have to provide a lot of energy. So this electron gain enthalpy will be positive, and it would be the most positive among the entire period. So electron gain enthalpies of halogens are the highest, but that is the negative electron gain enthalpy, which means that in a period, the halogen is the atom which it is easiest to add an electron to them. And the positive value of the electron gain enthalpy of the noble gas would also be the highest, again, because it would lead to a very unstable configuration. So this was about the group 17 and group 18, that is halogens and the noble gases. If you go down in a group, on the whole, what do we see? The ionization enthalpies, they are slowly, the negative value is 141, 200, they're all negative values, minus 195, 190 and 174, which means the negative value is decreasing on the whole. But we find these exceptions here, that is sulfur and chlorine. Oxygen and sulfur, if you see, sulfur has negative ionization electron gain enthalpy of 200 and oxygen has negative electron gain enthalpy of 141, which means that when oxygen gains an electron, it does not release as much energy as sulfur does, which means, and I just told you that the smaller an atom, the closer are the electrons to the nucleus. Therefore, the electron which is adding should be attracted by the nucleus even more strongly. And therefore, this should have had a higher value. The negative value only indicates that the energy is being given out. The amount of energy is the numerical quantity. So, you would expect sulfur to release lesser energy than oxygen. Also, you would expect chlorine to release lesser energy than fluorine, because in fluorine and oxygen the electron is adding to the second shell, but in sulfur and chlorine it is adding to the third shell. But then why do these release more energy while oxygen and fluorine do not? This exception is seen only in the case of second shell. The second shell, the first shell only has s orbital. The second shell only has s and p orbitals. It has only 4 orbitals and a capacity of only 8 electrons. So when you are trying to add, it's very, very close to the nucleus. So when you add an electron, the nuclear charge remains the same. And since the nuclear charge is the same, you're pushing in an electron into it. And since you're forcing an electron, the repulsion between the electrons becomes so large that the amount of energy given out is not as much as you would expect. So these exceptions are in the case of oxygen and fluorine. So this was the general trend in ionization, in electron gain enthalpy. As we move from left to right, the negative value of electron gain enthalpy increases, and as you go from top to bottom, the electron gain enthalpy, it increases towards the top, which means if you go from top to bottom, it decreases. The negative value of electron gain enthalpy decreases. So this was electron gain enthalpy. So let us now come to the next property, that is electronegativity. Electronegativity is a property which is actually a comparative property. Like in a tug of war, the team that is stronger would pull the rope towards itself, and the team that is weaker would not be able to pull the rope towards itself. So electronegativity is actually a property in which an atom, when it is bound to some other atom, what is its tendency to pull the shared pair of electrons towards itself? That is a measure of electronegativity. In covalently bound molecules, we'll study about chemical bonding later. A covalent bond is formed when two electrons are shared between two atoms, or a pair of electrons is shared. One of these atoms would have a stronger tendency to pull the electrons towards itself. Maybe because of its higher nuclear charge, maybe because of its lesser screening effect. Whatever be the reason, the atom may have a stronger tendency to pull the electrons towards itself. So whenever such a bond is formed, the atom which has a higher tendency to pull electrons towards itself, the pair of electrons moves slightly towards it, thereby making the other atom slightly positive, while this atom becomes slightly negative. Very partially. This property is known as electronegativity. That is the property by virtue of which an atom has a tendency to pull a shared pair of electrons towards itself. So you would expect, you can grade all the elements, and you would expect one element to be more electronegative than the other, and the expectations are right because of whatever properties we know. But how much of that electronegativity does it display depends on the difference between the electronegativities of the two atoms which are combined together. If the difference is smaller, it may not be so pronounced. But if the difference between their electronegativities is large, the pull of one of them would be so strong that you would actually feel that the atom is not covalent, the molecule is not covalent, it is ionic. So this is a tendency of an atom to pull the shared pair of electrons towards itself. Now, since it is a comparative value, there is no proper scale to measure it. But there was one scale given by Linus Pauling, and it is called the Pauling scale, on the basis of which we allotted values to all elements. And out of all the elements present in the periodic table, fluorine is known to have the highest electronegativity value, and that is 4 on the Pauling scale. The electronegativity value of fluorine is the highest. It means whenever fluorine binds itself to any other element covalently, it will have a tendency to pull that shared pair of electrons towards itself, and this tendency is the highest or the strongest in fluorine. So fluorine, whatever other element it combines with, would always pull the electron towards itself. But if you have other elements which have electronegativities which are lesser than this, then if they combine with an atom which has a higher electronegativity, the one which has higher electronegativity will pull its electrons towards it. But if it combines with an atom with lesser electronegativity, it is this atom which will have a tendency to pull the electrons towards itself. So it is a comparative behavior. Like in a game, if you're playing with someone who's stronger than you, you will lose the game. But if you're playing a match with someone who is weaker than you, then you have the tendency, you have the strength or the capacity to win the game. So which one? It depends on what is the atom bound to. But on the whole, if we try to see the trend, if we see the halogens, fluorine, chlorine, bromine, iodine and astatine, the values, the electronegativity values are 4, 3, 2.8, 2.5, 2.5. So we find that the electronegativity values, they go down as we go down a group. But if we compare the electronegativity values of a period, for example, lithium, beryllium, boron, carbon, nitrogen, oxygen and fluorine, we find that the electronegativity value increases on the Pauling scale from 1, 1.5, 2, 2.5, 3, 3.5 to 4 in fluorine. So as you move from left to right, the tendency of an atom to pull the shared pair of electrons towards itself increases, and as we move from top to bottom, the tendency of the atoms to pull the shared pair of electrons towards itself in a covalent bond decreases. So these were the different periodic trends in physical properties. I would like to summarize these just once more before we move on in the next video to the chemical properties and their periodic trends. What are these? The properties. We studied that in the entire, if this is the entire periodic table, the non-metallic character, it increases diagonally, or rather from left to right, the non-metallic character increases, and also from bottom to top, it is the non-metallic character that increases. So on the whole, you find the trend to be like this, that the non-metallic character is increasing as you move to the top right. And metallic character is the opposite. As we move towards this left, from left to right, the metallic character decreases, and from top to bottom, metallic character increases. So we find that this diagonal tendency or trend is seen in metallic character. The atom which is in the bottom of the alkali metals should be the strongest metal, and the element which is on the top of the halogens here should be the strongest non-metal. And they form basic or acidic oxides on the basis of this tendency. We'll study about that later. The other property is, as we move from left to right, the atomic radius, it decreases. As we move from left to right in a period, the size of an atom decreases. So the atomic radius decreases, or these arrows are towards that side where that property is increasing. So atomic radius increases from right to left, or we can say from left to right, it decreases. Electronegativity increases from left to right. And atomic radius, it increases from top to bottom, and electronegativity decreases from the top to bottom. Then electron gain enthalpy. The electron gain enthalpy is the amount of energy which is given out when an atom gains electrons, or it is gained. The negative, when we are talking of negative electron gain enthalpy, I would say the energy which is given out. So the amount of energy which is given out when an atom gains electrons increases as we move from left to right, and from top to bottom, the electron gain enthalpy decreases. And ionization enthalpy increases as we move from left to right. That is, the amount of energy required to pull out the most loosely bound electron increases as we move from left to right because of the decrease in size. And from top to bottom, we find that the ionization enthalpy, it decreases. Why? Because the size of atom increases and it becomes easier and easier to remove the electron from the outermost shell. So these were the periodic trends in physical properties. In the next video, we'll do the periodic trends of chemical properties. Thank you for watching. If the video helped you, please like it, subscribe to my channel, recommend it to your friends, and please keep returning for more videos in chemistry. Bye-bye.